Alright, so we have been discussing this gradient and vanishing and exporting problem in the previous part, right? Then next we can move to a new part on the LSTM. This LSTM can be used to address this gradient vanishing and exporting problem effectively for the recurrent neural nets. Let's do a revisit of these recurrent neural nets again. How to define the hidden neuron representation and how to calculate the output. So based on the recurrent neural nets with both inputs as well as the neurons in the previous part, then we can define the hidden neuron state and HT according to the formula we show at the bottom, right? So for the HT, we can define its representation based on both the raw inputs XT as well as the hidden neuron state from the previous one, the HT minus 1. By combining them together, we can define HT equals to, we have sigma mode, this activation function, inside we have UXT, right? Denoting the inputs from the raw inputs plus with WHT minus 1, the previous neuron inputs plus with bias term. This is a recurrent neural net we showed before. Also, according to the previous page discussions, this kind of updating process we are suffering from the gradient vanishing and exporting problems potentially, right? Then we may consider how can we address this problem by resolving this gradient vanishing and exporting problem for the recurrent neural nets. And one of the ways we can address this problem is by utilizing this LSTM. What is the LSTM? LSTM, the full name is called non-short-term memory. This LSTM can be used as something like a neuron. In other words, by using the LSTM as a neuron, we can also composing a recurrent neural nets, right? So before this one is a neuron, and by using this neuron, we can building a recurrent neural net as shown in this page. Similarly, by treating this LSTM, this block as a neuron, we can also build one recurrent neural net with one single hidden layer as shown here, right? Given the raw inputs as well as the hidden layer shown in this one, we can learn the representation of all the inputs like HT, right? And this HT will receive inputs from both the raw inputs XT as well as the previous input from the previous neurons, right? This one, right? Then we can update the hidden representation of the current neuron layer by layer, also neuron by neurons, and so forth, right? However, compared with the previous page, this LSTM, this neuron will have a much more complex architecture. Inside it, we can see we have so many different components, which seems to be very complex. So also different from the previous one. The previous one, we only have one single input from the previous neuron, like HT minus 1, right? However, for this LSTM, we have two lines here. This line and this line. They will feed in different inputs to the LSTM neuron from the previous one. This one denoting some cell state. This one denoting the hidden state of the previous neuron state. And we can show you one by one of this architecture for you. So let's have a look at the first line we draw here in the very beginning. So in the LSTM, we draw one line connecting different neurons. We call this line denoting the cell state. We denote this line, this variable carried by this line or this belt as CT. It denotes the cell state. It can also be called this long-term memory. So the LSTM introduces CT, the variable, to represent the cell state by different neurons in the architecture. So it receives the cell state from the previous one, CT minus 1, and then it will be used to update its current CT, cell state for this neuron state. So the cell state is something like a belt. It runs straight down in the entire chain with only minor linear interactions. It allows the information to flow along the chain without many changes actually. So of course, based on the information we receive from the previous neurons as well as the raw inputs, we will further update the cell state based on both the CT minus 1 as well as other inputs we show here to calculate CT. In the following pages, we will discuss how to define the CT based on inputs, inside the LSTM. Okay, besides one, let's have a look at another input, which is this line. So LSTM will receive inputs from both the raw inputs XT as well as the previous neuron hidden state HT minus 1. This is the hidden state. This one denoting the cell state. It's different. So the hidden state is more like short-term memory actually, and the cell state denoting the long-term memory. So based on HT minus 1, the hidden state as well as XT, we can define one gate in the LSTM. So inside LSTM, we define one gate is called forget gate. So for the older cell state, LSTM needs to decide which information to be discarded or to be thrown away actually. Therefore, LSTM introduces a forget gate defined by the FT as shown here. We can define the FT according to the inputs received from both the previous neuron as well as the current raw inputs. So based on both these two inputs, we can define the ft is gate as defined by the formula as we show here. So this operator denoting the concatenation between two vectors ht-1 and f and xt. By concatenating them together, also parameterized by wf and bf, this denotes the weight and this denotes the bias. We can define one gate for forgetting some of the information. This will be a gate and subject to the activation function like signal function as shown here. So this gate will be utilized to adjusting the cell state. We will show this later. So we have defined one gate, for adjusting the state, and the gate is defined based on the hidden state as well as raw inputs, right, as shown here. And this one will be, all the entries inside the forget gate, it will be a value within the range from 0 to 1 actually, because here if we use signal function, right. So this ft will be a vector for the input, right? All the entries inside the ft, this vector will be in the range from 0 to 1 because here we have signal function, right? And if the entry, the value or the gate value is close to 0, it denoting we will forget this value from the cell state. And at the same time, if this value is very large, like approaching to 1, then we can preserve this kind of information state. We can show you this later. So by concatenating this X raw inputs as well as the previous hidden neuron state, we can define the forget gate as shown here. Besides the forget gate, we can also define some other gates in LSTM, like the injection gate. So for the older cell state, LSTM needs to inject some new information from the inputs. Therefore, we will define one injection gate, which is also defined based on the raw inputs xt as well as the previous hidden neuron ht-1. In a similar way, we can concatenate these two vectors, xt as well as ht-1 together. We can define the injection gate. Here we are subject to the wi and bi as the parameters denoting the weights and the bias. Also, we have the signal function as the activation function. We can define this injection gate will be a vector. Inside, we have all the entries. This value will be in the range from 0 to 1. This is another gate, and we'll show how to use this gate later in the following pages. Besides this gate, the injection gate, we also define another variable like c tilde t. What is c tilde t? It's denoting the pseudo cell state for the current LSTM neuron. So this c tilde t is defined purely based on the inputs xt and ht-1. In a similar way, we can concatenate them together, then define this kind of c tilde t according to the formula we show here. We have parameters wc and bc, and also we have tangent as the activation function. We name this one as pseudo cell state, and it is computed based on new inputs we show here, right? So now we have introduced two gates, the forget gate, the injection gate, as well as one pseudo cell state. They are all defined based on the raw inputs as well as previous hidden neuron states, right? Then in the next page, we will show how to calculate the current neuron hidden state as well as the current neuron cell state. Okay, so first of all, let's have a look at how to update the cell state based on the gates we defined before. So in this page, we show you the cell state updating process by fusing the old cell state as well as the newly computed cell state. The pseudo cell state we showed before, right? Based on the input, we can update the cell state. And the fusion weights are decided by the forget gate as well as the injection gate. I hope you still remember we mentioned for the forget gate, it decides which information in the old cell state should be thrown away, right? How about the injection gate? It decides to inject some new information from the inputs into the cell state, right? Therefore, you can see in the formula, we define the cell state Ct equals to what? Equals to a combination of the old cell state together with new cell state. This Ct-1 denoting the cell state we have received the input as input from the previous neuron, right? This one denoting the newly calculated pseudo cell state in the previous page. By combining them together, we can define the current neuron cell state. And this combination is weighted, and the weight is decided by both the forget gate as well as this injection gate. It controls which kinds of information will be thrown away. This controls which kind of information should be injected into the CT, right? So by combining them together, we can define the CT denoting the cell state for the current neuron. I hope you can follow me, right? In this way, we can fuse the long-term memory together with short-term memory to define the current long-term memory for this neuron, right? This is the way we define for the CT, the cell state. How about HT? The HT calculation process will be very similar. It will be very similar. So first of all, we have to define one term OT. It is also a gate. It is also a gate. And this gate will control which part of the information in the long-term memory will be preserved to define the current short-term memory. So we define the OT as a gate, also based on the XT and HT minus 1. By concatenating them together, also subject to the WO and BO as the parameters, then we can define this OT gate. This neural gate will be filtering the cell state and to define the short-term memory or the hidden state by formula as shown at the bottom. We have OT defined by the gates, right? We also define a CT in the previous page, denoting the long-term memory for the cell state of the current neuron. And part of the information can be filtered and used to define the hidden state for the current neuron. In other words, we define HT equals to the OT, and we have this element product between the vectors, right? OT and this result by the cell state. So you can see in this way we can define the HT, the cell state, according to both the output gate as well as the cell state we defined in the previous page. I forgot to mention this star denoting the element-wise product between two vectors. It's not convolution we showed before, right? So we use this star here to denote this element-wise product instead. So, by going through this architecture one by one, then you should be able to understand how this architecture works and how to define and how to update both the cell state as well as the hidden neuron state, right? One by one and step by step. So in this way, we can calculate both the CT and HT at the output, which will be serving as the output to both the following neurons as well as neurons in the upper layers. Okay. So the reason why this one is called LSTM or the long-term short-term memory, because we have two parameters inside the neuron, the CT and HT. The CT is something like a long-term memory. It carries all the information from the previous neurons, right, and until the current one. And this HT is called short-term memory, because this one is mainly decided by the raw inputs XT as well as HT minus 1. This is much shorter than the previous one. So by combining CT and HT, then the neuron will be able to capture both the long-term memory as well as short-term memory in the learning process. And you may also wonder how this kind of LSTM can handle this gradient management problem. Then let's have a look at this problem we mentioned before again. We mentioned why this gradient vanishing and exporting problem will be very serious for the recurrent neural nets. We show you the main reason by formula we show here, right? The main reason is because when we calculate the gradients for the recurrent neural nets, we have two terms to worry about. The first term is for this W, right? This W is raised to the power of T prime minus T as well for the activation function, right? We mentioned if this W is a very large number or very small number, then this term will be either growing very fast or decaying very fast. Similar for the activation function as shown by this term, right? It will also decay actually if we have not so activation function to be times together as shown here, right? Then how about the problem when it comes to the LSTM? And when it comes to the LSTM, remember for the cell state, the CT, we represented it as a combination of both the old cell state as well as new cell state. And the summation weight is decided by these two gates, right? Then you may wonder, how about the gradient of this cell state, among the neurons? At the bottom part, we show you the gradient of the cells at the T prime neuron versus the T neuron. By calculating the gradient of this T prime neuron, the cell state versus the T neuron cell state, we can define an output to be the product of this gate, right? Of this gate. So in other words, its result will be denoted by the gates as we show here. Remember, this gate is defined based on secondary function. In other words, its result will be the product of all the values in the range from 0 to 1, right? It can effectively address the gradient management problem, also the exporting problem effectively. So by introducing this gate, then we can handle this information integration very effectively, also address this gradient management problem and exporting problem in the learning process for recurrent neural nets. Okay, so this is LSTM, And in the next page, we'll show you another version of the neuron, which can further simplify this LSTM, this neuron. And we'll discuss how to use the LSTM and the new neurons to build these deeper recurrent neural nets.